My test marks in calculus have been in the 70s.
Ah, fair enough. Can't argue with numbers. Okay.
Apparently, calculus you can't. You do everything with numbers in that.
So you disabled it?
Yep.
Of course you did.
Think how much easier calculus makes physics. Think about it, right? Like you want the velocity, it's just the derivative of the position, right? Oh, sorry, other way around. You want the position, it's just the derivative of the velocity. You want the velocity, it's just the derivative of the
Acceleration.
acceleration. You want to go the other way, right? Like you want to know the acceleration, it's just the integration of the velocity,
Whoa.
right? Like it's funky stuff,
Horrible. It's hard.
right? Like
Real hard.
so, area of a circle, it's just the surface area of a sphere, rather, it's just the derivative of its volume, right? Like it's great.
I feel so comfortable with it all during the unit. I sit down to do the review and I'm like,
I took first year calculus for the math major in the summer once in the States, and that was a mistake. That was one of the. I know how you feel because that was one of the. Not one of my best marks in university, let's say. If I have one more sound effect come in this room, you're gonna see a tantrum. We had a fire alarm last period, and then we got back. I'm like, all right, we're gonna try and power through this lesson. Then the lawnmowers started, and I was complaining about the lawnmower, and then the weed whackers started. I was like, oh. Yeah.
Start yelling.
It's like I'm sweaty. It's humid in here. It smells like grade 9, which is fine. We were all there one day.
It's gonna smell like grade of 12.
That's right. Yeah. Anyway, that's right. Grade 12 senior is just the smell of fresh tears. No, there's no crying in baseball. Okay.
But we're not playing baseball.
Fair enough. We've been talking, well, one day. We've spoken about redox reactions. What's a redox reaction?
Oxidation or reduction.
Yeah, it's oxidation or reaction, and it's reactions that involve the transfer of electrons. Now, do you need a sheet? There you go. Do all reactions involve transfer of electrons? Not necessarily, right? So today we're going to talk about balancing redox reactions. The first thing we need to be able to do is identify redox reactions to know if they've taken place or not. And the way we do that is we look at a reaction and we look at the oxidation number, which we spoke about yesterday, right? We look at the oxidation number of everything on the left side of the equation. And we look at those same species on the right side of the equation. And if their oxidation number has changed, then we know that electrons have moved. If you guys don't mind, I'm planning on leaving the doors open for airflow. I was going to say, Roshlo, if you want to go out and scream when they get noisy, you've totally got my permission. You do what you got to do. But some guidelines, as a rule of thumb, with very few exceptions, we said hydrogen will always be +1, and oxygen will always be
Minus.
-2. That's okay. So when we look at these, we will tend to look at everything but oxygen and hydrogen. So in this first reaction, that's easy. What are the two species we're talking about here? Zinc and sulfur. And we're just going to look at its oxidation number on the left side and the right side, and at how it has changed. So that's okay. Those are far away. They're not like in front of the window. Who's on
Amy
this?
said that was
Okay, that's fine. Okay. On the left side, let's look at zinc. What's its oxidation number here? It's a stable atom sitting all by itself. What's its oxidation number? 0. Good. On the right side, it's part of an ionic compound. In an ionic compound, we just look at what its charge is in the compound. And zinc, when it makes an ionic compound, takes what charge? Very good. Oh, that appears to be a leaf blower.
So we were both wrong.
It's late enough in the year.
A leaf blower.
They got the orchestra.
Listen just to sabotage.
He's gonna come out with a tuba next, for God's sake.
Well, I mean, it's sort of a pretty practical thing to be using as a garden tool.
All right. So over the course of this reaction, how does zinc's oxidation number change?
+2.
Yeah, it goes up by 2. All right. Sulfur on the left side of this equation has what oxidation number? 0, because it's a stable atom. On the right side, it's now in an ionic compound. So we look at what its charge is in the ionic compound. And in an ionic compound, sulfur takes a charge of -2. So what is its change? -2. Sorry? We can, and they're going to sum out to 0 in this case, but that's not what we're worried about. What I would like to know, which of these is being oxidized?
No.
Zinc. Because remember, oxidation is a loss of electron, and if its charge is going up, it's losing electrons. And sulfur is being reduced. By the way, this table that we're going to use a lot makes this naming make more sense, doesn't it? Its oxidation number is reduced. So if the number is negative, that means that it has been reduced. Now I want to look at another example. And here we have sulfur. And we said hydrogen can change from time to time, but really, we're going to know that in this case, hydrogen we always treat as +1, oxygen is -2. So the only thing we really have to look at is sulfur. So let's look at it. In the left side,
So H2O is nothing.
well, hydrogen is going to stay +1. Hydrogen's oxidation number is always +1 in these reactions. So it's not going to change. Oxygen's oxidation number is always -2. We can write them in the table if you want, but they're not going to change. So let's look at sulfur here. Each oxygen gives us -2. And there's how many of them? For a total of -6. So to bring this thing up to 0, what must sulfur be? +6. Good. Yeah. So to find sulfur's oxidation number, thank you. We look at oxygen. Oxygen is always -2, but we have 3 of them. So that's a total of -6. The whole number has to end up being 0 because this is a neutral atom. So to bring this up to 0, sulfur must be +6. And on the right side, each oxygen is -2, and we have, so that's -8. But each hydrogen is +1, and we have 2 of them. So that would bring us to -6. So the sulfur must be +6. What's the change? There is no change. So if there's no change, this is not a redox reaction. Still a chemical reaction, still occurs, but it's not a chemical reaction that involves moving electrons around, changing charge. So once we've done this, we can start talking about actually balancing redox reactions. Now, when we balance a normal chemical equation, we need to make sure that there's 6 atoms on the left and 6 atoms on the right. If there's 5 hydrogens on the left, we need to make sure there's good. And if there's 4 nitrogen, there need to be good. Redox reactions, we talk about how many electrons these things gain and lose. And we need to make sure that's balanced as well. So if nitrogen is going to lose 4 electrons, then we need to make sure that sulfur is gaining 4 electrons. Those need to balance, yes? Possibly.
Yes.
Everyone on the cart should. They always did. I don't think the minis do. You could check the minis. Well, you know what? I feel like no, because they didn't have the password for the minis. Well, check them, because the minis did come pre-imaged. So they may.
So other than that, would it have been the library ones?
It was definitely these ones, but they re-imaged them in September. Why they would re-image them without those apps on them is beyond me, but it was definitely these ones. I've done it before. There were always a couple that didn't have it,
Yes.
but like of the 10, 8 had it.
Remember, like, 4 or 5 of them
I bet you there
Had all 3.
had frog or rat or both.
Yeah.
Just, purple bypass with 3D brain.
No, not so much, but do check the minis. So I have this feeling that they were preloaded with science apps, but I may be wrong. I'm often wrong. I'm frequently wrong, but occasionally right. So no, actually, no, that's not true. Like next time you're on a plane and the pilot goes, from time to time I get these landings right. It's not going to make you feel good. Yeah, most of them go poorly. Nothing, that stinks. No way. That's unfortunate.
This is not true. Never right. Yeah, because he's married.
Wow, that's a cynical view. How old are you?
What?
That's a cynical point of view. People always say that. I always, this is totally tangential, but there's nothing I find more frustrating than, I've been to a lot of weddings because I used to work at a place that did weddings. So I usually attended about 30 a summer, which is awful. I mean, I didn't attend, I worked at them, but the point being, I was managing the place for about 30 weddings and each summer, and I was there for 4 years. So that's a goodly number of weddings. And there's this thing that everyone always gives his speeches where they talk about how, I guess sarcastically, but how awful it is being married at a wedding. And I think that's really depressing. That's a really miserable point of view. No, I have found that, my wife is a very agreeable person. I'm a very disagreeable person, but she puts up with it. And that's about it. But I don't know, it's a pretty good gig. And she cleans and does my laundry and I cook, and it's a nice balance. I do the dishes, she builds stuff, I break it. It's a great arrangement. So the first step every time is we're going to look and make sure that this is indeed a redox reaction. So we're going to look at the left side, the right side, and see if there's a change. And again, we're not going to worry about hydrogen and oxygen because for the reactions that we're going to see in this unit, they will
Not change.
You should probably complain about it a little. I think it'll help. No, please. Give me a couple more. No, you're done? Okay. We'll move on then. So let's first look at nitrogen. In this species here, what is nitrogen's oxidation number?
What species it was?
Gonna be positive 1.
Nope. Definitely not positive 1.
5.
I like +5.
Oh, sorry, there's a 3 on that.
Yep.
Okay. Yep.
All good. Yeah, I like +5. Can everyone see that? 3 oxygens, that takes us down to -6. 1 hydrogen brings us up to -5. And so to cancel that, we have to be +5. Yeah, you have to look at this whole molecule. Now, what species on the right has nitrogen in it?
NO.
NO. What will its charge be here? Or its oxidation number, pardon me.
Positive 2.
+2. So what's its change?
-3.
-3. Because it's with oxygen. Oxygen is -2, so the nitrogen must be +2. They have to cancel each other out. Did you do last night's homework? That's okay. Go through and do that first because it's just practice finding the oxidation numbers. It is straightforward stuff. Once it clicks, you'll be like, oh, I totally get it. I promise. Okay, and then we're also going to look at arsenic. So Stowe, I'm going to pick on you. I'm not going to pick on you. That's not true. But we're going to go through this together, okay? So arsenic on the left side is in this molecule. So we need to find out what its oxidation number is. The whole thing has to add up to whatever its charge is. Does this have a charge? No, so this has to add up to 0, okay? Now what we know is that oxygen is always -2. How many oxygens do I have here?
3.
So what's that give me? Good, -6. Each hydrogen is always +1. And how many of those do I have?
3.
So I have -6 and +3. What's that give me?
3.
-3, right? Does that make sense?
Yeah.
So then the arsenic has to cancel that. So to cancel -3, it must be Well done. Do you want to try it again on the right side?
Here.
Okay, so let's look at this one. I like to start with the oxygens.
Oxygen is -2, you said?
Yep.
So that's -8.
Good.
Hydrogen will be +3 again.
Yep.
So that leaves you with -5.
Yep.
So then that must be negative.
Almost.
What?
You want to cancel.
-5. Oh, so you add 5?
Very good. That's right. Good job. And what is the change in this case then? +2. Now this should lead you to two conclusions. What are the two conclusions we can make from this?
There's a charge.
There is a change, which means what kind of reaction is this? Okay, so it is a redox reaction. What other conclusion do we make here?
It's not balanced.
It's not balanced, right? As this reaction is happening, nitrogen is gaining 3 electrons, but arsenic is only giving up 2 electrons. So that doesn't work. So even though, if you look at the equation, arsenic and nitrogen are balanced, we have 1 nitrogen on the left, 1 nitrogen on the right, 1 arsenic on the left, 1 arsenic on the right. They're not balanced because their electrons aren't balanced.
So now you have to balance the other
Yeah,
side.
and what we need to do is figure out the ratio. All right, so I guess we already did this above, but what is the ratio here? What is the lowest common multiple of these two things?
2.
So we have the number 2 and the number 3. What's the lowest common multiple of those? 6. So we need to use some number of nitrogen and some number of arsenic so that these two will be the same value. I guess I should put like the absolute value, lowest common multiple. Don't worry about it, doesn't matter. Now for that to be true, to get to 6, how many nitrogen am I going to need and how many arsenic? Yeah, I'm going to need 2 nitrogen, and that will give me a -6. And I'm going to need 3 arsenic, and that will give me a +6. Is that reasonably clear? Because that real step is the whole trick of this lesson. The rest is pretty elementary. So now what we're going to do is rewrite the equation, but we're going to make sure when we rewrite the equation that we have, oh, that's not what I meant to do. There we go. I'm even going to make it a little bigger. Hey, there we go. Okay, so have fun rewriting it, suckers.
Steven, write this for me. No.
Okay, so now we're going to go through and make sure that we have 2 nitrogen on each side and 3 arsenic on each side. So on the left side, what do I need to do to make sure I have 2 arsenic? Or 2 nitrogen, rather. I'm sorry. I like that. What do I need to do to make sure I have 3 arsenic on the left side? Good. What do I need to do to make sure I have 2 nitrogen on the right side? And to make sure I have 3 arsenic? Good. Oh, time to plug in. It's more fun walking around, but that's okay. Now, at this point, we just need to look and make sure it's balanced for any simple redox reaction. And this one, what are we going to have to, I mean, the only thing left that we might have to balance is what? What's the only thing we haven't put a coefficient in front of? Water. So we may or may not have to balance the water out. Let's take a look. How many hydrogens on the left side?
6, 8.
Yeah, well, I know. 3 times 3 is
9.
9, and 2 times, and 2, so 11. And how many on the right side?
11.
11. Okay, so I like that. And what about oxygen? How many on the left side? 15. How many on the right side? Don't forget that one. 15, good. So in this case, it is already balanced. We can leave it alone. Obviously, it won't always be the case that you don't have to put a coefficient in front of whatever's left over. In this case, we don't have to worry about it. Yes? Yes, and in fact, we're going to talk about those cases next.
Library iPad channel.
Sorry?
Library iPad channel.
That's bizarre. You know what? At the end of the year last year, when Nikki took all the iPads and sorted them, I wonder if some of ours ended up as theirs and some of theirs ended up as ours.
No, you know what it was though? Because it was the green cover that I remembered, and those are the green covers.
Well, at least we have them.
Yeah. But maybe for next year we need to send them off and say, hey, there's nothing useful on these.
Now, just like Ms. Radko very astutely observed, you can have a situation where no matter what you do, that last coefficient, in this case on the water, won't balance the whole thing out. And that's true. Some redox reactions happen in acidic solution. They end up working out in such a way that we get acidic solutions. We know this, for example, if anyone has ever left a battery sitting in a remote control for too long and come back and seen it, and it's that, has anyone done this before? And you get that white gross paste that's corroding the metal. That paste is corroding the metal because that paste from inside the battery is highly acidic. Eventually it corrodes its way through the battery and then starts corroding its way through your piece of equipment, which is unfortunate. That's the challenge, right? You need metal terminals on the battery to carry a current, but that metal cap eventually gets corroded by what's inside. So this is an example of how we balance a redox reaction, a redox reaction that nets an acidic solution. And the example we're going to look at is chlorate ions reacting with iodine in aqueous solution. So again, what are the two species that we're going to concern ourselves with here? Good, chlorine and iodine. And we're going to look at the left side, the right side, and how big a change that is. On whom should I pick? No. Mashinsky, can I pick on you? Okay. Okay, let's look at chlorine on the left side, Mashinsky. What charge does this, what oxidation number does this have?
Oxygen is 3 of them, -2, that's -6, but it has a charge of -1, so we plus 5.
Wow, masterfully done. Very good. I was wondering if the negative would trip you up. It did not. So keep in mind that if the whole thing has a negative charge, then instead of them adding up to 0, in this case, they have to add up to -1. The oxygen gives us 6 negative, so to get to -1, we need 5 positive. Good. And on the right side, sir?
-1.
Yeah, don't overthink it. Perfect. What's the change? Yeah, it's gone down by 6. So it's reduced. So if it's reduced, obviously the iodine is going to have to be oxidized. Can I pick on someone for that?
Kyle.
McGowan, go. What is its oxidation number here? Good. And here?
+6.
Is it?
No, it's not. 2, 4, 6, -5.
Good. Very good. So what's its change?
+5.
Good. Very well done. Okay, now. So what is the lowest common multiple in this case? Yeah, the lowest common multiple is going to be 30. And what ratio of chlorine to iodine will give us that ratio, or that common multiple? How many chlorines do I need to get to 30? Great. And how many iodines do I need? Good. So a 5-to-6 ratio. So we need to rewrite the balanced chemical equation, making sure that we end up with 5 chlorine and 6 iodine.
Yeah, right? Okay. So isn't it just flipped for the,
Here's the deal. You can always just flip them. It may not be the lowest common multiple, right? This is like, remember when you had to find the lowest common denominator? That you could always just multiply the two numbers together, and that will give you a common denominator, but it might not give you the lowest common denominator. If you just flip these, it'll always work. You may just end up reducing your whole equation later on. But long story short, it will always work to flip it. You'll never be wrong to flip it.
but that may not be the lowest.
It may not be the lowest, so you may end up having to reduce your whole equation by having it later on. In other words, you may end up with a balanced chemical equation at the end that was like 4 of this, plus 2 of that, plus 6 of this, plus 8 of that, and those would all be divisible by 2. But you'd still have a right answer. You just have to take a look at it at the end. Does that make sense?
Yeah.
Cool. Kyle.
Why is the chemical equation, why do we have Cl negative and the IO3? They're both negative.
Yep.
Wouldn't one of them be positive because it's also?
Nope. Not necessarily. These are both anions. So there would have been cation spectator ions associated as well. And this, by the way, says aqueous, but should actually be gas. This happens when you bubble a gas through a solution. Which would tell you why the reaction actually happens, right? Because otherwise you'd be like, but shouldn't it just be? Anyway. Okay. Now we have to rewrite the equation with this multiple in mind. So we need to make sure we have how many Cl's? 5. Okay, so what am I going to do to this? Good, so 5ClO3. We need to make sure I have how many iodines?
6.
Good, so what am I going to put in front of this?
3.
Good. And we need to make sure we have 5 Cl's, so. And we need to make sure we have 6 of these, so.
6.
For clarity's sake, I'm going to drop all of the state subscripts. In our final answer, we should make sure we remember to put them back in. All of the aqueuses and gases and things of that nature. All right, now if we take a look, we should see, of course, that chlorine and iodine are balanced. What isn't balanced? Oxygen. How many oxygens on the left side? Damn friggin' oxygen. How many on the left side? Sorry, on the left side? Yeah, and on the right side? 18. Okay. So, there is no way we can manipulate these numbers to balance both the electrons and all of the atoms. Can't be done. So don't try. But where is this reaction taking place?
Water.
In water. These are aqueous solutions. So the water can become involved in the reaction. In this case, water is going to have to react to provide enough oxygen for this reaction to take place. Which side is going to need to use oxygen? Yep. Good. How many of them?
3.
Good. Well done. So we're going to add 3 waters to the left side of this equation. And so it will become 5ClO3 minus plus 3I2 plus 3 water is going to yield 5Cl minus plus 6IO3. Now, the astute amongst you will note there's no hydrogen. But this is not a problem. In fact, this is an explanation. We said at the beginning that when this reaction happens, the solution becomes acidic. So what are we going to find on the right side of this equation?
H plus ion.
H plus ions. How many of them? Yeah, if we take a quick look, we will see that we have 6 hydrogens on the left side, none on the right side. And so we would now say 5ClO3 minus. What is? It's the worst what? Yeah. Okay. You know what? That S in that right side is like a person too. Like it had its own hopes and dreams and fears. And how do you think you made it feel about itself, saying that it was the worst one you'd ever seen? Like what? Apparently in Amy's world, every S has to be the same shape and size and have probably the same religious views. And you know what? Like, yeah, that's right. You know, in the big wide world, some S's look alarmingly like straight lines. It's so hard to believe about that. Anyway, I'm going to try to stop thinking about how judgmental that was and just keep writing the equation. But not for me, for humanity. All I'm saying is, like, if I want to express myself through Q's that look like squiggly lines or G's, depending on the day, who are you to tell me I can't? Concerns. Well, I appreciate your concern.
Oh, just for my learning, so I can tell what is happening.
I'm only kidding.
I appreciate the concern, but it does for the as well. I understand your issues. I just don't.
My wife took a class in like one of her classes in university that they had to take for her major was like conflict management. And one of the phrases they were taught to use was, I appreciate your feedback and I'm going to, what was the, I hated the language. So it's set an intention and I'm going to set an intention to consider it. Set an intention. What does that even mean? What a butchery of the English language, but there you go. That's what you're supposed to say when somebody offers you feedback, and you want to politely say, like, drop dead. Anyway. Okay.
Report it. Yeah, then you call it confidence and do dumping it.
When I was, I don't know why I'm telling the story, but when I was in high school, my friend Jesse was the first of us to get his license and a car. And he had this eggplant purple Daytona. Who made maybe a Chrysler Daytona? Whoever made this car called a Daytona. This thing was hideous. It eventually met its end a few months later when, and this is true, its wheels, singular, its back right wheel just fell off on the highway, which isn't something you want happening. But before that, it used to billow these great voluminous billows of smoke. Anywhere he took it, it was noisy as you could imagine. Like this thing just, it shook like the thunder of the gods. And you drive down the road, and it should have been embarrassing, but we were just young and excited to be driving. Anyway, my friend Jesse is a real character, and you don't see things like this nearly as much now. And I think you didn't see it as much when I was a kid as like maybe in the '60s. But we were at a stoplight at Lake Street and Scott Street in St. Catharines, and it's 2 lanes at the time. And the people next to us just shoved a McDonald's bag just out their window and just left it. And so Jesse opened his door, grabbed it, and we went like halfway through the city till we could eventually get beside these people again, and he threw it back through the window. I don't know, I'm telling you, there's no point to this story. That just made me think of it. Anyway, at the time, it seemed like a clever thing to do. You know, they didn't seem impressed, but we drove away in a billow of smoke and like the sound of the hammers of the gods, you know, receding. You know, the wheel like. Daytona. Who made Daytona? Is it a Chevy? I don't think so. I feel like it is a Dodge. Or like Dodge Chrysler. Dodge Daytona? Yeah. It's alliterative. It's people like alliterative. Oh, okay. This is clearly subjective.
Chevy Daytona.
Did they both make a Daytona? Can you just do that? You just steal other people's names? Like, could I just make like?
There's also a Dodge one. Look at the ugly one though.
Like, could I just start making Honda Civics and just go?
Look
at that. Okay. I'm saying, can you just do that? Can you just steal like names and go? Anyway, let's focus. Okay. Okay. So when some redox reactions occur, gentlemen, they occur in such a way that they release H+ ions, which makes them acidic. Acidic. Okay, Kyle. Be quiet, gentlemen. Thank you. Some reactions, of course, don't just occur in acidic conditions. You can also have them occur in basic conditions. We have some reactions that are basic. So the second example would be, and here we're going to use methanol reacting with permanganate ions in a basic solution. By the way, just before we go, methanol is an alcohol. Primary, secondary, tertiary, methanol. Primary. If we mix a primary alcohol with permanganate, potassium permanganate is what kind of agent?
An oxidizing.
It's an redox reaction. It's an oxidizing agent. What does the alcohol become? Yeah, it does. It becomes a carboxylic acid. You're right that first step, it will become an aldehyde. And then the aldehyde will further be oxidized. Yeah. So look at that. Yeah, it all comes together. So, don't judge me. So, first thing we need to do, we know that this is a redox reaction, but we're still going to go through the steps of determining what the change is. So, what are the two species that we need to be concerned with here? Carbon and manganese. Okay. Let's take a look at carbon on the left side. What is its oxidation number? What do we got?
-2?
I don't know. Yes. Yeah, looks like it. Because the oxygen will be -2. The 4 hydrogens will bring us up to +2. And to cancel that out, carbon must have -2. What about on the right side? What's carbon's oxidation number?
+4. And I still leave the last part.
Trust your instincts. Which I understand is just telling you, but somehow that feels less like
It's
telling
like
you.
I get this one because it tells you which direction it
Yeah.
is, but I don't know what.
Yeah, trust your instincts. Worst case scenario, you're horribly wrong. What is the oxidation number of carbon here on the right side?
+4.
+4. What's the change then?
+6.
+6 altogether. And manganese on the left side, what is its? Radko, what do you got? Radko, did you make a mistake in pen? I'm sorry. I can give you a fresh copy if you want. What do we get?
It's +7.
Yeah, I like +7. 4 oxygens give us -8. The whole thing has to be -1. Yeah. So the whole thing has to add up to -1. So the manganese is +7. +7 plus -8 is -1. Okay, it happens. Kyle, why don't you try the right side? That's right.
So the oxygen is -8.
Yep.
So 6.
Very good. And what's the change then? Very good. Okay, so what is the ratio then in this case? The lowest common multiple is what? And the ratio of carbon to magnesium or to manganese is what? Because I want to have lots of space to write the equation. Because I won't be put in a box calmly going. Nobody puts baby in a corner. I'll dance if I want to. How many carbons?
1 to 6.
Very good. Well, yeah. It's clearly one of the greatest films of all time. No, it's a great movie. Come on. Yeah, no. You can, like, when you're younger and a guy, you feel like you have this moral obligation to pretend you don't like dancing movies. Then you hit a certain age and you go, that's really great. I'm going to step up to the streets. Try and stop me. Anyway. Which, like, is just a pale shadow of the original. Not a better sequel. Anyway. And don't even get me started on Havana Nights, because it just, yeah, that just didn't do the trick. No, yeah, not impressed. Anyway, so let's go ahead and put these into the equation. Every time we need to make sure we have how many carbons? Unos, good. Okay, so here. How many?
1.
There you go. You found your words. And how many of these? Good.
That's a lot of
Don't be rude. Okay, and how many CO3s?
1.
And MnO4s? By the way, it's worth of note, remember we said potassium permanganate doesn't get used up in this reaction? It doesn't, right? Do you remember that when we talked about, it's not, here's the thing, it is part of this reaction, and then it will later get itself back to its original charge by reacting with the water in solution. That's a separate reaction. But, oh, you're right, I did. But that's why potassium permanganate is considered a catalyst, not part of the reaction, because after this reaction, its next step is to regain its original oxidation state by reacting with the water around it. And so at the end of that reaction, it's right back where it started, and it can be used again to carry on the reaction. Remember that? How when we did these reactions in our organic unit, we wrote it over top of the arrow? That's why. I just want to explain why there we said it's just a catalyst, but here it seems to be changed. It is changed. It gets changed back by the solution itself. Anyway, and another redox reaction. Now, what do we notice here? Well, we're going to follow the same steps as last time, which is we're going to add water to balance the oxygen atoms, and we're going to balance H plus to balance the hydrogen atoms. Okay? So we're going to do the same thing, because the reaction is going to work the same way. It's going to react with the water in solution, and that's going to produce H plus ions. So we're going to deal with water first, oxygen. How many oh, geez Louise. How many oxygens on the left side? 25? And on the right side? 6 times 4 is 28, 24, 27, good. So how many do we need? Okay, what am I doing here? Just stop. So we need to add 2 waters. Okay, and then once we've done that, let's also look at hydrogen, because I'm going to do them all in one step this time. How many hydrogens on the left side? There's 4, and then we're going to add 2 waters, so there'll be a total of 8. Does that make sense? Stop me if it doesn't. And then what about the right side? How many are there right now? Sorry? Nope, because we're only adding the water to the one side. Right? We're making up the balance with H plus ions. Yeah. So we need to add 8 H pluses to the right side. What is?
Oh, God, every
Okay, can we focus? Doing chemistry here, thank you. Yeah, you set it up. So now, sure you do. You know KSP, and then you know what these two things are in this breakdown. So make an IC table. That's my only guess. Make an IC table. No, it means that charges 2 in that contact. Yeah, it just means that in iron sulfide, the charge on the iron is 2. Crisscross rule, you know that. Just forget things. Okay, now here's the problem. Here's the problem. In this reaction, if this reaction were happening in acidic solution or just in neutral water, it would make it acidic solution, right? This reaction makes H pluses. Is that clear? Okay. The problem is, what is also available in basic? So if we did this in an acid or a neutral water, this would be the reaction. But at the top of this note, you're going to see that this is actually happening in a basic solution. If we are in a basic solution, will these be allowed to just sit around? No. Right? If we produce new H plus ions, they are going to react with the OH minus that are present in basic solution. So if a reaction like this happens if this happened in neutral, if this happened just normally, we'd be done. This is where we would have left off in the last section of this note, right? But here, we now have to keep in mind that those H pluses will get canceled. Okay?
How do we know that it's acidic or basic?
I would have to tell you.
Oh.
I would tell you that that a permanganate ion reacts with methanol in a basic solution. So it is nothing to do with the reaction itself. This has to do with the reaction conditions. This has to do with where we make this reaction happen. But if this happens, what is going to cancel out those H pluses? OH negatives. Okay. And so what we're going to do in this case, scroll it up. This way?
Yeah.
Good. Sorry? Oh, I had them. If you look, I put a little note on the bottom. I shamelessly pilfered this note from somewhere else because I didn't like mine, and I changed it a bit because they had too many steps. This went to like step 9, and I thought that's too many steps. We can intuit a few of these at once.
Is that the right unit description? Yes, is all
I was gonna
Yeah,
say, this is
Yeah, no, this one is stolen. This is not my intellectual property. But I liked it. I thought it was pretty good. It was better than what I had, so I stole it.
At least you didn't pass them.
I mean, I would have if I hadn't thought of it. But like, just to be clear, some of the stuff you get, I steal. Most of it I make myself because I'm finicky and I like things a certain way. But in this case, I liked things a certain way and it sucked. So I thought, I got to find something better than this because this is going to have people like glazed over in no time. So now this step is the tricky one. But basically, I want you to imagine that this is happening with OHs present. Lots of OH around. Can we imagine that? Who's chilling out? Yeah, it's just chilling out. How many OH minuses is it going to take to neutralize those H pluses? 8. Does that make sense? So we are going to add 8 OH minuses to the left side. And on the right side, those H pluses are going to become good. The H pluses will become water. Does that make sense? So if we redid that whole reaction, but this time we had OH minuses available on the left side at the beginning, instead of getting H pluses at the end, we'd get water at the end. So we would have CH3OH plus 6MnO4 plus 2H2O yields, oh, plus my 8OH minus. Sorry, that's the whole point of this step. Yields that carboxylic acid, 6 MnO4s, and plus 8 waters. It seems so much more laborious because we're stopping and talking about it. When you actually get doing the questions, it just kind of happens quickly, right? This feels long because we're stopping to talk about every step and then talking about unrelated crap because I can't keep focused. Now, the last thing I want you to notice is what? Yeah, once we've done this, we already had 2 waters on the left, but now we have 8 waters on the right. So what is the net change in the amount of water? Yeah, so these 2 will cancel with 2 of those to give us 6 on the right side. And that's the final balanced equation. And try to remember when you get to the final balanced equation to put back in all of the subscripts of state. Nope, because they're not. Is that MnO4 minus 1? Yeah. At some point, I just stopped writing that.
So if it's a basic solution, you're still
So again, what we want to be clear is the reaction itself, again, was an acidic reaction, wasn't it? The reaction itself released H plus ions, but in a basic solution, we would have to be mindful that those H plus ions wouldn't be allowed to stick around. So if I had given you this same question, but said it happened in an acidic solution or happened in neutral water, you would have been done after step 3, right?
You just had to keep going.
But you will get situations where it says this reaction happens, but it happens in a basic solution. And in those situations, you need to be mindful of that and make sure that you don't leave any H pluses sticking around, but that you're sure to react those with OH minuses. Questions about that? Comments, concerns, thoughts, prayers, hopes, dreams? Yes.
Are you going to be teaching anything tomorrow?
I mean, it could be debated how much I teach things any day, but I'm going to be talking. I'm going to be up here and I'm going to be making noise. And you're going to be right or not if you're not here. But listen, if this room is empty, I'm pressing record and then teaching the lesson. And you have my blessing to do what you like, believe me. I was young and wild and carefree once too, but I am forging ahead, one way or the other.
I could just see Ramona sitting here talking to the afternoon.
Oh, listen, that is precisely what I will do.
Asking questions, waiting for responses that never come.
I might impersonate you. Actually, if none of you show up, it might be the most enjoyable class I've taught, because I will, you want to see something really funky? So my son showed me this.